units and conversions. That's what this final lesson in a chapter on measurement in my high school chemistry playlist is going to be about. This will include like metric conversions and dimensional analysis and things of the sort. We started this chapter off with a lesson on significant figures and then scientific notation, and then finally precision accuracy. And like I said, we'll be finishing it off with this lesson on units and conversions. Now, this is my brand new high school chemistry playlist. I'll be releasing these videos weekly throughout the 2020-2021 school year. So if you don't want to miss one of these, be sure to subscribe to the channel and click the bell notification so you're notified when I release new ones. The metric system. So if you're from the same country I am here in the good old US of A, then you're an idiot, first off, and you're an idiot by birth. You don't even know it, but you haven't been using the metric system, and the metric system is a beautiful thing. It's all nice powers of 10. It makes calculations real easy and stuff like that, and instead we're like, there are 12 inches in a foot. Well, who decided that? How did we decide how big a foot was? Well, because that's how long the king's foot was. And the problem is when that king died, another king was born, then the length of a foot might change. Well, that's not very convenient. Whereas everything in the metric system is all beautiful powers of 10. And so while you might not be as familiar with them if you're from this country or possibly the UK or something like that, they are your best friend when it comes to doing calculations. And so one of the unfortunate things is that we haven't adopted the metric system, and I don't see it happening anytime soon. It would be a little bit of a pain in the butt to do so, but that does cause problems every once in a while. We had one of our Mars rovers back in the day that had some problems because some of the people working on it were using the metric system, and one particular contractor that was working on it was using the British Imperial System, and didn't realize they weren't using the same units. And as a result, this thing crashed and burned on Mars and did not carry out its function, and lots of money down the tubes because they didn't check their units, so to speak. So this can be potentially a big issue and stuff like this. So if we take a look quickly at the SI set of units, so SI stands for Système International. So, and these are the French people that kind of set the units. So, and there's more debate on this than you think in terms of how they define these units and stuff like that, but I'm not going there. But there are a few we just want to define here. So I want to make sure I'll put them up on the screen here for you. So the SI unit for length is the meter, so little m. So lowercase m is the symbol for that. So for mass, it is the kilogram. And that's an interesting point of note. The SI unit is actually the kilogram. And in a physics class, you're going to use that a lot. So, but in our chemistry class, we'll much more commonly just use grams as a convenient unit for mass. Time, SI unit is the second. Temperature, it is Kelvin. So, and Kelvin may not be something you're completely familiar with. So, if you're in this country, we use Fahrenheit a whole lot. So the rest of the world, they use Celsius a whole lot more. And that's much more convenient because the conversion between Celsius and Kelvin is simple. You just add 273.15 to your Celsius temperature to get your Kelvin temperature. So on a nice balmy day, we might have 30 degrees Celsius. And it turns out if I want to express that in Kelvin, so we just add 273.15 to this, and we end up with 303.15 Kelvin. So again, we just added 273.15 to our Celsius to get our Kelvin. If you wanted to go back from Kelvin back to Celsius, you'd subtract off 273.15. Now, one thing to note, most people just kind of throw away that 0.15 and they just say add 273 if you're going from Celsius to Kelvin, or subtract 273 if you're going from Kelvin to Celsius, and that's usually sufficient. So from here on out, you'll probably never see me tack on that 0.15 ever again in this conversion. Now, if you were dealing with converting Fahrenheit to Celsius, you've got this extra factor of like 5/9 or 9/5 and this extra 32, and we're not going to go there. Most of the time, we just leave Fahrenheit out of this discussion altogether. So, and we'll be dealing with Celsius or Kelvin pretty ubiquitously throughout the course. So, and that's typically a way any general chemistry course works. We just throw Fahrenheit out the window. So pretty much all the major units we use in the US here, just throw them out the window. We're going to start over, although you will, on occasion, because we use them so often, have to use them or convert them to the metric system quite often. So it's going to be a little thorn in your side here. And for those of you that are from almost any other country in the world, you're like, this metric system, got it. It's what I use every day. So, but again, for those of you in the US or possibly the UK, in the UK, they actually use it pretty much more often than we do as well. So, but pretty much for us idiots in the US, sorry. It's going to be a little bit of a pain in the butt here at first. Cool. After temperature, we've got an amount of a substance, and the mole, and we'll have a whole chapter to define what the mole is and different calculations involving it, so I won't cover it here, but it is an SI unit. And then I've got a couple grade out there, the electric current, so amperes, and we won't use that pretty much in this class, except maybe once at the very end. And in that case, truth be told, probably not in this playlist, maybe for more of an AP playlist as well. And then luminous intensity, the candela, we won't use that in this class at all. So, but those are your 7 fundamental SI units. I've also put a handful of derived units. These are all derived from those 7 fundamental units. And it turns out that the SI unit for volume is the meter cubed, and we may not use that at all in this course. Much more commonly, we're going to use liters. And it turns out there's 1,000 liters in 1 cubic meter, or 1 meter cubed. So, but it turns out if you're using SI units, like you might often in a physics class yet again, the SI unit technically is the meter cubed, or the cubic meter, not the liter, just an FYI. So just want to make that distinction as well, because again, one key place again in volume, in addition to like we saw in mass, where we're not often in chemistry going to be using an SI unit. Energy work is the joule. We'll use that a time or two. And then pressure is the Pascal, and that's another place where in a typical chemistry class, we might use Pascal here and there, but way more commonly we're going to use atmospheres and torr and millimeters of mercury. But the Pascal is technically the SI unit. In a physics class, you'd use it fairly often, but we'll use atmospheres probably more commonly than anything else, and torr and millimeters of mercury. And when we get to a chapter on gases, we will explain all that then. Just suffice it to say, I did want to point out your SI units and where we often use different units in a typical chemistry class. All right, let's talk a little more about that metric system. So your metric system is based on a series of prefixes, and you can put any one of these prefixes on a number, or on a unit, I should say, and it changes the value of that unit. So if you look at like the meter, so let's say I've got 1 meter, we'd write that with a little lowercase m. Now, if I want to say that I have 1,000 meters, I could say 1,000 meters, but there's some alternatives here as well. So I could also say that I've got 1 times 10 to the third meters. That'd be another way to say it with scientific notation. I might actually, if I was really trying to do proper scientific notation, make it 1.0 times 10 to the third meters. But the truth is, if I only had 1 sig fig, I'd have to keep it as just 1 times 10 to the third. I could also just get rid of the 1 entirely and just write it as 10 to the third meters, because anything times 1 is the same number. So this is really the same thing, just 10 to the third meters. But I do have one alternative as well. And if you look over here, this little k here, right here, lowercase k, stands for kilo, and it itself means 1,000. It means 10 to the third. And so another way to write this would just be simply to write 1 kilometer, or 1 kilometer here. So because this means 1 times 10 to the third meters. That's the way this works. And so we've got a whole host of different units we can use depending on the situation and stuff like that. And this is really convenient for a variety of things. So if if you asked me, hey, Chad, how tall are you? And I said, I'm 5'8". You're like, well, and you're like, just express it in inches, Chad. And I'm like, I'm 68 inches tall. Great, no big deal. But if you instead asked me, hey, Chad, how many miles tall are you? And I'd look at you and be like, I have no idea, like way less than 1 mile tall, but it wouldn't be a convenient unit to use here and stuff like this. So same kind of thing. If I said, hey, how far is it from here to the moon? Like the Earth to the moon. And I want you to measure that in like millimeters or micrometers. Well, that's not the most convenient unit. You'd want to use some much larger unit for that much longer distance. And the metric system allows us to scale any kind of unit in any way we want to maybe use something more convenient for the measurement we're making. So, but that does present us a dilemma, and you've got to be able to convert within the metric system from any kind of unit to any kind of prefixed unit as well. And we'll definitely spend some time going over that. All right, so we've seen this introduction, and these you just simply have to memorize. Now, the truth is, I added some extras on the bottom of this scale and the top of this scale. So, but we've got peta, tera, giga, mega, kilo, centa, milli, micro. Notice that lovely symbol right there. Kind of looks like a U most of the time, but it's really a funky Greek M. We call it mu. So, and then nano, pico, femto, atto. So most of your classes for high school, you're probably never going to see femto and atto, and you're probably never going to see peta up here as well. So I just included them all on here to be thorough. So, but if you're taking this class in high school or something like that, just go with whatever your teacher says, whatever boundaries they give you. So, and if you're taking this like for a homeschool or something like that, suffice to say, if you can go from tera to femto, that will suit you well in the future. All right, so let's talk about conversions now. Now that we've seen this metric system, and talk about how we actually carry out a variety of different conversions in some of the different units we have. And so got a series of questions on there, and the first is convert 84 inches to feet. So, and I apologize for all the rest of the world. I'm kind of catering to the US a little bit here. That's kind of my typical audience. But we're going to go inches to feet. And I wanted to start with something that you're more likely to be a little more familiar with, how big that is and stuff like that. And so to go from inches to feet, what you want to do is take your conversion here, and you want to make sure you put the units in the denominator here to cancel out the ones that are in the numerator over here. Because when I multiply through, those units are going to cancel. We call this dimensional analysis, by the way. And then the unit you're converting to, you'll put in the numerator here. And the big thing here for any conversion factor is it just needs to be an equal, in this case, length expressed in two different units. And we know what that is. We know that 1 foot equals 12 inches. So, and when you do this, then the inches here are going to cancel, and this is going to come out in feet. And in this case, we'll take 84 and divide by 12, and we're going to get 7 feet. So now in this case, we should, if we're going to express this in proper proper number of sig figs, we should look back at the original number and say, well, it's got 2 sig figs. And a lot of students want to go look at our conversion factor here and be like, well, this one, 1 foot, that's only got 1 sig fig, Chad. Well, sort of not actually. So is there like approximately 12 inches in approximately 1 foot? No, there's exactly 12 inches in a foot. So, and for a conversion factor like this actually means that we have 1.0000000, and you can keep saying O's for the rest of your life. That's how many feet we have in 12.0000000 inches. So that's the equality we're giving here. So we assume that in conversion factors, they have an infinite number of sig figs. Now we see with some of our more complicated ones, they actually might be an approximation, but we're going to treat conversion factors as always having an infinite number of sig figs. And as a result, they're not going to affect how many sig figs we should express our answer. And so in this case, all we're doing is multiplying and dividing. And the only relevant number then is the original, which has 2 sig figs. And so the truth is we shouldn't actually write this as 7 feet. We should write it as 7.0 feet. That way we're expressing it in 2 sig figs. Cool. And there's our answer. And again, I just wanted to show a very simple one here. So if you look at the other one on your handout, we're going 2.5 feet to inches. So if I want to convert this to inches, that means I want the feet to cancel. So now we'll put the feet on bottom. We want to convert to inches, so we'll put the inches on top. And now we'll put 12 inches over 1 foot. So notice you might have the feet on top and the inches on bottom if you're converting to feet, but you might have the inches on top and the feet on bottom if you're converting to inches. The key is that your conversion factor can be used either way. As long as these two quantities are equal, that's what you need for a good conversion factor. And so in this case, our feet will cancel. So, and 2 times 12 is 24, and another half of 12 is another 6. That gets us up to 30. And so this is going to equal 30 inches. But we have a problem. 30 inches only has 1 sig fig, and my original number has 2 sig figs. And again, I won't consider the conversion factor itself for sig figs, just the original number here. And so in this case, I need to express this in 2 sig figs, and I have 2 options. I can include the decimal, which I personally just hate doing, or I can write this in scientific notation, right? 3.0 times 10 to the 1 inches. Let's make that one a little more obvious. Cool. And that's what I like doing, is just writing everything in scientific notation when I'm, wondering about having to write a decimal in or something like that. It's just easy to go to scientific notation instead and get your proper number of sig figs. All right, let's do some more of these. So we've got 1,500 meters to kilometers. And to make this work then, so I need the meters to cancel, so I will make sure the meters end up in the denominator, and I want to convert to kilometers, so that'll be in the numerator, and this is kind of how I set up my conversions. I always do the dimensional analysis part first, setting up the units. So, and from here, we have a problem, because there's really two different ways to do this, and I'm going to show you both, and I'm taking a risk here, but I want to show you both just in case somebody else ever shows you both. But after I show you both here, I will never do it both ways ever again. I will choose one way, and I'll choose the way that makes a little more sense in doing it. So, however, I will let you know that having been doing chemistry for well over 25 years, I do it both ways in my head all the time, depending on what I'm converting and stuff. So it'll get convenient. It's just a matter of convenience. But for presenting it to students, I only show it one way. All right, so in this case, it turns out if you want to use what the actual prefix means, so then you're going to have a unit without a prefix in any conversion you do. At least that's what I'd recommend. There's a way to not do it. If both units you're converting to and from both have a prefix, there's a way to do that in one step. I'm going to recommend you do it in two, and we'll do an example of that later. But in this case, you're going to have a unit with a prefix and one without a prefix. The one that has the prefix in this case, so in this case, that prefix being kilo, that's where you're going to put a 1. Every time. This is the way I always teach it. And then the one that has no prefix, that's where a power of 10 is going to go. And what power of 10 is going to go there? Well, the power of 10 that your corresponding prefix means. And in this case, K for kilo means 1,000 or 10 to the third. And so that's why we're going to put 10 to the third right here. Cool, and that works. 1 kilometer equals 1,000 meters. That's what a kilometer technically means. Kilometer, 1,000 meters. So 1 kilometer equals 1,000 meters. That's a conversion factor, and it totally works. So if we actually work this out, so 1,500 divided by 10 to the third is going to get us 1.5 kilometers. In this case, my original number, these two zeros, are left of a decimal and end the number. They are not significant, so it's only the 1 and the 5. So 2 sig figs, my answer is going to end with 2 sig figs. All I'm doing is multiplying and dividing. So that's actually expressed in the proper number of sig figs. Now, the other way to carry out this conversion, you still would have had to put kilometers up top and meters down below. But the other way to have done this is to put 1 meter here, and it turns out 1 meter is 1/1000th of a kilometer. And that's totally a true statement, and this will still get you the right answer. If you divide by 10 to the third, that is no different than multiplying by 10 to the minus 3. So there's actually two ways to carry out any metric conversion, which is really more of a pain in the butt than it's worth. And so the problem is that there's two different ways that work. And so students, if they're presented with both, often do one versus another. Well, we're not going to do this. I choose to do the way where the power of 10 I use is the definition of the prefix itself. So first thing you might have to notice here is that, yes, you have to have all those metric prefixes memorized and what power of 10 they correspond to. And again, when we do this, then every time there's a prefix with a metric to metric conversion, that's where I'm going to put the 1. And then the unit that does not have a prefix, that gets the power of 10. Cool. If you do it backwards, you're going to get it wrong. And you'll find out that, with a unit that corresponds to a number bigger than 1, like 1,000 here, this is the way we would do it anyways. But you'll find out when we start getting some of these units that are smaller, oftentimes it's more convenient to do it the other way around if you're doing it in your head and the way you think about it. However, I will never do it that way. So you often catch many professors and teachers and TAs and things of this sort who don't, because we just do it the way we're doing it in our head, don't realize they're presenting two different ways at different times to students, only screwing them over royally. So I will never, ever again do this again in any of these videos, just as an FYI. Cool, let's look at another one of these. So right next to that, we've got 32.1 kilometers to meters. Cool, we'll put kilometers in the denominator, we'll put meters up top. And once again, where you see the prefix, that's where the 1 is going to go. And where there's no prefix, so in this case meters, no prefix in front of it, that's where the power of 10 goes. And kilo, once again, means 10 to the third. And so in this case, if I've got 32.1 kilometers, then we'll find out that we have 32,100 meters. And again, my original number here's got 3 sig figs, and my final number here's got 3 sig figs. Those zeros ending a number, so left of the decimal, are not significant. Just the 3, the 2, and the 1 are significant. So 3 sig figs, life is good. All right, let's look at a couple more here. So convert 0.34 kilometers to millimeters. Okay, so we want to go from kilometers to millimeters, and you might see that we have a problem, because you might be like, well, I want to go from kilometers to millimeters. And here it is, one metric unit to another metric unit, but these both have a prefix. And you're like, well, Chad, you haven't showed us how to do this. Well, they both have a prefix, and you're right. So who gets the 1 and who gets the power of 10? You're not going to know. And there is a way to carry this out, and I don't even teach this to like freshmen in college. Usually you got to be a little more advanced as a chemistry major, and we'll work with this. It's not hard, but it's definitely not where you want to start. And so in this case, we're not going to go this route. What we're going to do is do this in 2 steps. We're going to first convert kilometers to meters, and then we'll convert the meters to millimeters. And this way, every step of our conversion involves the base unit that has no prefix. Kilometers and meters, meters and millimeters. So both of them involve just plain old meters with no prefix, and now we're good to go. And so once again, where you see a prefix, that's where the 1 goes. So kilometer has a prefix, millimeter has a prefix, that's where the 1 goes. And where there is no prefix, that's where the power of 10 is going to go. In this case, kilo again means 10 to the 3rd, whereas milli, looking back up here, that's the little m here. That's actually a capital M for mega, but milli means 10 to the negative 3rd, or 1/1000th. And we look at this, our kilometers cancel here. That's why we put kilometers in the denominator. The meters will cancel here, and we'll be left with an answer in millimeters. And so we're going to multiply by 10 to the 3rd and then divide by 10 to the negative 3rd. And the effect of that is actually the equivalent of multiplying by 10 to the 6th. So and we'll just move this over 6 places. And so we're going to get a 3 and a 4 for sure. And it'd be 1, 2. But we got 4 more places to move over. So we're going to have 4 more zeros. And we got 340,000 millimeters. All right, our original number's got 2 sig figs. And our final number also has 2 sig figs, so this is expressed in the proper number of sig figs as well. All these zeros are insignificant because we're ending a number and they're left of the decimal. Okay, let's do one more here. So we've done everything in terms of length so far, so I definitely want to do something in terms of another common conversion you'll see, and so we'll do one involving volume. And in this case, it says 0.245 liters, 2 milliliters. So in this case, liters to milliliters. So we'll put liters on bottom, milliliters on top. So in this case, it involves a conversion involving one of the units having no prefix, so where life is good. And in this case, the unit that has a prefix gets the 1, and the unit with no prefix gets the power of 10. And once again, milli means 10 to the negative 3, or 1/1000th. Cool, and our liters will cancel, and we'll get an answer in milliliters. And dividing 0.245 by 10 to the negative 3 is the same as multiplying by 10 to the 3, and so this is going to come out to 245 milliliters. So, and eventually a conversion like this, oftentimes one we just do in our head because, dividing by 10 to the negative 3rd is the same thing as multiplying by 10 to the 3rd, and multiplying by 10 to the 3rd is just simply moving the decimal 3 places to make the number bigger, which is what we did. 1, 2, 3, and we got 245. Now, I chose this example on purpose because this is one of those places that when I do this in my head, or any kind of seasoned chemist or chemistry teacher does this in her head, we often don't do it this way. So we would do it the other way that I said I would never do again. So I just wanted to give you a place where you might see somebody explain this. Instead of doing 1 over 10 to the negative 3, they might do 10 to the 3rd over 1, which again, I'm not doing. So because I want to make sure I'm consistent in using the prefixes exactly as they're defined instead. So next, we've got to take a look at conversions involving area and volume. And this is a little bit of pain in the butt. And this is a place where students often make a mistake. So definitely pay attention here. So if we take a look at area, and so I'm going to first just take a look at the area of a square. And I want to take a look at it in units you might be familiar with. So let's just say it's a square where each side in the square is 1 foot. And my question for you at home, or wherever you happen to be, is what is the area of this square? Well, you might recall the area of a square is just side squared. And so in this case, 1 foot times 1 foot, and the area of this square would be 1 foot squared, or 1 square foot, we'd say, because 1 foot times 1 foot is 1 foot squared. Great. So no big deal there. And so if I asked that, hey, what's this in inches squared? The biggest mistake students make is often say, well, then that would be 12 inches squared. Well, that's actually not true. And you can see that it's not true pretty easily if I actually express the length of each side in inches. Well, 1 foot is 12 inches here, and 12 inches here. And 12 inches times 12 inches is not 12 inches squared, it's 144 inches squared. And so the key is, if you want to take this 1 foot squared and convert it to inches squared, what you do is put feet down here, inches up here, and to be like, 1 foot is 12 inches. That's what normally students want to start by doing. And the problem is the foot here does not cancel the foot squared here, for one. And also, we want an answer in inches squared, not just plain old inches. And so this conversion factor is insufficient. And what we've got to do to make it sufficient, though, is just square the entire conversion factor. It squares the 12, so you get 12 squared right there. It squares the units, so you get inches squared. And it squares the 1, and 1 squared is still 1. And it squares the feet, so you get feet squared. And now the units will cancel. And because we're multiplying by 12 squared, we'll end up with our 144 as well. And so there's our 144 inches squared, or square inches, however you want to say it. All right, so this applies the same way in the metric system and stuff like this. So in this first example, we want to convert 1,200 centimeters squared, or square centimeters, to meters squared. And so in this case, we'll just use our standard kind of conversion. We'll put centimeters down below, meters up top. That way, these have a chance of canceling. But notice, again, it's not going to quite be the right units. But centimeters has got a prefix, that's where the 1 goes. Meters has no prefix, that's where the power of 10 goes. And centa means 10 to the negative 2. But again, these units aren't quite going to cancel here. And to make sure we have the appropriate units and stuff, we've got to square the entire conversion factor. And again, that squares the numbers and the units. Everything in there gets squared. And now we'd have centimeters squared and centimeters squared. That'll cancel. And we'll end up with meters squared, just like we're trying to get to. So, but in this case, instead of multiplying by 10 to the negative 2, we're going to be multiplying by 10 to the negative 2 squared, which is 10 to the negative 4. And so as a result here, we're going to move this back 4 places, 1, 2, 3, 4, and this is going to equal 0.12 meters squared. 2 sig figs in the original number, 2 sig figs in the final answer, so that is properly expressed. So that's the deal with area. So you just have to remember that your original conversion factors are not adequate to make the units work out the way you need them to, and so you need to square them to make that happen. Now, something similar happens with volume. Now, volume can be measured very commonly with like liters and milliliters and things of a sort, in which case this would not be part of this conversation. But you might recall that the SI unit for volume that we'll use very seldomly is the meter cubed, or cubic meter. And so you might end up with volume being expressed in terms of like length cubed, in which case you have a very similar problem like we saw with area. And so if I wanted you to convert this to meters cubed, once again, a lot of students look at this and they're like, okay, I'll put meters here. I'll put centimeters here, and I'll put meters on top. And where there's a prefix, I put the 1, and where there's no prefix, I put the power of 10. And again, centa means 10 to the negative 2, and then that's all they do. And they multiply 1,200 times 10 to the negative 2, and they get the wrong answer. But again, my units are not set to cancel at all. In this case, I've got centimeters cubed here, but only got centimeters. And so in this case, to make the units work out properly, I need to cube the entire conversion factor. This would be 10 to the negative 2 cubed, which is 10 to the negative 6, meters cubed, 1 cubed, which is still 1, and then centimeters cubed. So when I factor that in, I'm actually multiplying by 10 to the negative 6, which is going to move this, and again, just work this out in your calculator. So, but if you want to reason it out, this is going to move this, making the number smaller by moving it 6 places. So that's 1, 2, 3, 4, 5, 6, and we'd have to throw in a couple of zeros to make that work. So we're going to get 0.0012 meters cubed. 2 sig figs in our original number and 2 sig figs in our answer. The zeros in both cases are not significant. Cool, that's area and volume. And again, this is a common place students make an error, so by all means, get a little bit of practice when you're doing conversions, specifically with area and volume. All right, so one more set of conversions that's a little more difficult than what we've done. And this involves when you're doing conversions that involve not just metric to metric conversions or not just US and US conversions, but when your conversions involve starting with like a US unit and ending up in a metric, or starting with a metric and ending with the US. And so to carry this out, you have to know a conversion factor that expresses a US unit into a metric or vice versa. And that's not usually something you have to memorize. That's usually something that's going to be provided to you. Now, you might have to know that there's 12 inches in 1 foot. Cool, we expect that. That's on you. That's US to US. You might have to know that 1 centimeter is 10 to the negative 2 meters. That's metric to metric. So, but we don't expect you to know that there's 2.54 centimeters in 1 inch. That's something we're not going to make you memorize. That's something we typically provide with you. And so in this case, we want to convert feet to centimeters in this case. And in parentheses, you might notice that I told you that 1 inch equals 2.54 centimeters. This is provided, and it expresses a US unit in a metric unit, and that's what we're going to use as a conversion factor. If you call it a conversion factor, is just equal unit or equal measures in different units, expressed in different units. And so that's what we'll use. And so in this case, if I want to go from feet to centimeters, I have to recognize, oh, feet, that's a US imperial or US customary unit, I should say, and centimeters, that's a metric unit. So we're crossing over systems. And for that, I like to call this a crossover conversion factor. And I get to centimeters from inches. So if I don't have inches on the US side of things, then I better get there. And that's the first thing we'll do. We'll go from feet to inches. And I personally just like setting up the units part of this for the dimensional analysis. So we'll convert feet to inches. So, and then we know how to get from inches to centimeters. And so the next step in the conversion will involve inches. I'll need those to cancel, and getting to centimeters. So, and then we fill in the numbers. And so in this case, 1 foot is equal to 12 inches. So, and then this conversion factor is just what we have right here. 1 inch equals 2.54 centimeters. Cool. And then we just plug and chug and let our calculator do the work for us. So in this case, we've got 0.75 times 12 divided by 2.54. And we get 3.54 and a bunch of other stuff, but I'll round to the 3.54 for a second. And the question is, how many sig figs should this have? Well, again, in our conversion factors, there's exactly 12 inches in 1 foot. These are infinite number of sig figs. Now, the truth is there's not exactly 2.54 centimeters in 1 inch, but we pretend that these conversion factors are exact. Turns out this is a much longer decimal number if you want to carry it out. But the custom here is that in any conversion factors, treat the numbers within those as having an infinite number of sig figs. So in this case, the only number that really matters then is this first one, which has 2 sig figs. So I need to round this to 2 sig figs. So that means the 3 is going to be a sig fig, the 5 is, but the 4 is not. And this 5 is going to stay a 5. It's going to round down, so to speak, because the 4 is less than 5. And so expressed properly, this is 3.5 centimeters in the correct number of sig figs. Okay, so that's first pain in the butt here. Second place you might encounter a little bit of a pain in the butt in conversions is if you're doing more than one conversion in the same problem. And so in this case, I'm giving you a velocity or a speed here, 55 kilometers per hour. So, but the question's asking you to convert this to meters per second. So, and this problem is no harder than anything we've done so far. In fact, it only involves metric conversions for the most part. So it's no harder than anything we've done, except for the fact that it involves 2 conversions instead of 1. And either one independently is no difficult than anything you've seen. But for whatever reason, you put 2 conversions of the same problem, and all of a sudden it's twice as long as any other problem, but it's not twice as hard, but twice as many students miss it. So hopefully you get this straight. And it doesn't really matter which one you start with. We can convert kilometers to meters first, or we can convert hours to seconds first. It's totally our choice. So I'm going to start with kilometers, just my choice. And to do that, I'm going to put kilometers on the bottom and meters on top, and that'll make sure that my kilometers cancel here. So, and that's just a metric to metric conversion. We'll fill in the numbers later. So, but if I stopped right here, I'd end up with meters per hour, but we want to get to meters per second. So now we have to convert the hours part. And I can see here that hours starts off in the denominator. So to make it cancel, I need hours to be up here in the numerator. So And if you happen to know that there's 3,600 seconds in 1 hour, then you could do this in one step. But for most of us, we know the conversion between minutes and hours. There's 60 minutes in an hour. And so that'll cancel out the hours. And if we stopped right here, we'd have meters per minute. But then we want to convert the minutes to seconds. And to cancel out the minutes, we'll put the minutes on top in the conversion here, seconds on bottom. And finally, now we'll have meters per second. And now we just got to fill in the numbers. So between meters and kilometers, that's just a metric conversion. And a metric conversion, the prefix always gets the 1 in the way I do it. And the unit with no prefix gets the power of 10. And kilo means 10 to the third, yet again. And then between hours and minutes, 1 hour has 60 minutes in it. They're equal. And 1 minute has 60 seconds in it. They're equal. And now we're going to do some plugging and chugging. So I'm going to start with 55. So, and I'll do times 10 to the third, and I like doing times 1,000, but same diff. So, and then divided by 60, and you got an option here. You can divide by 60 times 60 if you put those two terms in parentheses. So, or you can just do divided by 60 and divided by another 60. Your choice, it works either way. So, but if you do have multiple terms you want to divide by, so if you're going to multiply them together but divide by the total, you definitely got to put them in parentheses here. But I'm going to get 15.3. So meters per second. So, and in this case, I've got 2 sig figs in my original number. All we've done is multiply and divide. So I want to end up with 2 sig figs in my final answer. And so in this case, the 1 is definitely significant. The 5 is, and that 5 is going to round down because 3 is less than 5. And so this becomes 15 meters per second expressed in the proper number of sig figs. Okay. So we're going to start with a fresh board here. So we've got one last little concept in this chapter regarding density. And we can make a separate video out of this, but I just want to tack it on to the end of this because it also involves potentially some conversions and stuff like that. So it often shows up in this context. So let's deal with density. Now density. There's an equation governing density. It's simply the ratio of mass to volume. And you can make a little algebra equation out of this, and that's usually the way I look at density. Instead of doing dimensional analysis, usually with density, I find students have a little better time with it if we just look at this as an algebra equation. There's 3 variables here. There's density, there's mass, there's volume. I give you 2, you solve for the third. So if I said, oh, there's density, well then what's mass equal to? Well, if you solve for mass here, you could see that mass, just multiply it by volume, is equal to density times volume. Okay, and if I said, well, solve for volume instead. Well, if you solve for volume, you'd have to divide by the density, and you get volume equals mass over density. And so regardless of which of the 2 out of the 3 variables in that equation I give you, you can solve for the third. You want to solve for density? Mass over volume. You want to solve for mass? Density times volume. You want to solve for volume? Mass over density. Cool, and you can derive them all. So definitely memorize this mathematical definition of density. It's something you need to know. So, and it's something we'll use right here. So a cube with 2 centimeter edges, and let's draw that out. So let's say it as it's written in the question with 2.00, I lost a 0 there, with 2.00 centimeter edges, weighs 10.0 grams. And grams is a measure of mass here. So in this case, what's the density? Well, we have the mass, so that's step 1, but we need the volume also to get the density. And so you're supposed to know what the volume of a cube is. Well, for a perfectly, rectangular cube like this, all sides are equal, and so it's 2 by 2 by 2. So, and the volume is just length times width times height, and 2 times 2 times 2 is 8. And so in this case, the volume is going to be 8.00, and centimeters times centimeters times centimeters is cubic centimeters. And so we definitely expect you to know what the volume of a cube is. So you should have encountered this somewhere in your academic career. And so now that we have both the mass given, and we've just calculated the volume, and having both mass and volume, we can plug them in to calculate this density. So density equals mass over volume, which in this case is 10.0 grams all over 8.00 cubic centimeters. So, and 10 divided by 8 should come out to like 1.25. and that would be grams over centimeters cubed. No units are canceling here. And we just say that this is 1.25 grams per cubic centimeter, or grams per centimeters cubed. And that's our answer. So our original numbers here, both the 8.00 and the 10.0, both of these have 3 sig figs. In 8.00, I'm ending a number with zeros, but to the right of the decimal, and they're significant. So in this one, I'm ending a number with a 0 to the right of the decimal, and it's significant, which makes the one in the middle significant. And so we have 3 sig figs, and all we're doing is dividing. And so we should have 3 sig figs in our answer, and indeed we do. Cool, so that's the first part of this question. The second part, though, says, how much would a cube of the same substance with 5.00 centimeter edges weigh? So now we want to consider a much larger cube. And the key is we're told it's the same substance. And that's important because being the same substance as the original smaller cube, it'll have the same density. So, and you might recall that we talked about intensive and extensive properties back in the first chapter on matter. So, and density was an example of an intensive property, which means it doesn't matter what size sample you have. It doesn't matter if you have a small cube or a big cube, the density is the same. And so that density we just calculated of 1.25 grams per cubic centimeter, that's not just the density of this small cube, that's the same density as this big one here. And the question is, what is its mass, right? How much would a cube of the same substance with 5 centimeter edges weigh? So in this case, if we want to solve for mass, it'll be density times volume, which in this case, the density is still that 1.25 grams per cubic centimeter, but we need the volume. And again, 5 by 5 by 5. 5 times 5 is 25, and times another 5 is 125. And so our volume is going to be 125 centimeters cubed. We'll plug that in right there. And we'll pull out our trusty calculator, and we got 1.25 times 125, and we get 156.25. So I notice grams per centimeters cubed times centimeters cubed, per centimeters cubed and centimeters cubed cancel, and we're just going to get an answer in grams. Now, we've got 5 sig figs in there, and that's definitely not the right number. So we've got 3 sig figs here, we've got 3 sig figs here, and so our final answer should only have 3 sig figs. And so that means the 1 is significant, the 5 is significant, and the 6 is significant, and that 6 is going to stay a 6. It's going to round down because of the 2. And so our actual answer expressed in the appropriate number of sig figs is 156 grams. Cool. This is the entire lesson on units and conversions. I hope you've found it helpful, and if you have, please like, share, subscribe, and if you've got questions, leave them in the comment section below. And if you're looking for practice on this or the study guide that goes with this lesson, by all means check out my premium course on chadsprep.com. Happy studying.